Hello, everyone. Good afternoon. Welcome again to, I think, one of the last early career scientist talks here at the ICCI Pavilion at COP29. This afternoon, we have Fabian Siemann, who's a PhD candidate at the Alfred Wegener Institute in Germany, and he'll be talking about permafrost environments in a warming climate. Take it away, Fabian.
Thank you very much, Shiva, for my introduction. And also, hello and welcome everybody to my presentation. My name is Fabian Seemann, and I'm a PhD candidate at the Alfred Wegener Institute in Potsdam, Germany. And my talk is going to be about subsea and coastal permafrost environments in a warming climate. So it is very well known that the Arctic is warming far faster than the global average. Since 1979, the Arctic has warmed nearly four times the rate of the global average. As a consequence, permafrost is warming, actually on a global scale. What is less known is that there's also subsea permafrost, and this domain also contains large amounts of organic carbon. So there's actually permafrost beneath the sea in the Arctic Ocean. Often overseen are also the dynamics of Arctic coastlines, which are very sensitive to climate change. Thus, the aim of my talk is to increase the understanding of subsea and coastal permafrost environments by explaining the subsea permafrost carbon distribution and potential of release. Also, I'm going to highlight coastal permafrost processes and implications for organic carbon. To better understand why we have subsea permafrost, we have to look back in time. About 25,000 years ago, during the last ice age, Eurasia and North America were covered by large ice sheets. This lowered their sea levels by about 125 meters compared to today's sea level. And it exposed the last vast Arctic shelves, such as north of today's Arctic shoreline in Russia, marked with the arrow, and also the land bridge between Siberia and Alaska, Beringia, was exposed as land. Today, the permafrost region covers about 22% of the land in the northern hemisphere, and also 2.4 million square kilometers of subsea permafrost remain, marked here with the arrow again. The Arctic Ocean is characterized by 34% of the world's coastlines. Permafrost sort of acts as a big freezer. Plant and animal remains have accumulated here over millennia, and it's locked frozen into the sediments. On the map, you can see in the green colors the terrestrial carbon pool, and in the blue colors the subsea permafrost carbon pool that remains here since the Arctic shelves got flooded with sea level rise after the last glacial maximum. And also, sedimentation continued here in the subsea environment, and as temperatures in the ocean are down to minus 1.6 degrees, we still persist here also permafrost conditions. When permafrost starts to thaw, microbial activity starts, and it eats up basically the organic matter that is stored in permafrost. In this process, greenhouse gases are being produced and released to the atmosphere. And I would like to put this a little bit into scale, how much greenhouse gases are actually being emitted to the atmosphere by thawing permafrost. So in this bar, you can see countries' emissions projected until the year 2100 based on their 2019 emissions. Current emission projections suggest that permafrost will cause additional emissions of 55 gigatons until the year 2100 under a low emission scenario. That's somewhere in the range between the emissions of Russia and whole Europe. On a high emission scenario, the emissions could even shoot up to 232 gigatons of carbon, which is somewhere in the range between the country's emissions of the US or China. The carbon budget that we have left to limit global warming to 1.5 degrees Celsius lies at 250 gigatons of carbon, which shows that the carbon bucket is already quite filled just with permafrost thaw and related carbon emissions. This estimation is based on an expert assessment accounting for a subsea permafrost carbon pool of 560 gigatons of carbon. Now I would like to present you some new numbers to that. In these bubbles, you can see the carbon pool of different spheres, such as the atmosphere, which stores about 880 gigatons of carbon in the blue circle. Then in the orange circle, you can see the terrestrial global permafrost region's carbon pool, which is almost twice as large as the carbon pool of the atmosphere. And the light blue colors are marking here the subsea permafrost carbon pool, which is based now on numerical modeling, which accounts for 2,800 gigatons of carbon, which are stored here. So again, a larger pool that is in the subsea environment. The subsea permafrost is characterized by slow warming processes, and the regulating factor for this is the sea ice distribution. As the sea ice continues to retreat, there's the potential of ocean warming, which would then also drive and potentially accelerate subsea permafrost thawing processes. But currently, the carbon emissions from thawing permafrost lie at about 0.05 gigatons of carbon per year. Now, compared to the emission scenarios based on this smaller carbon pool, which was taken into account previously, we can expect that these carbon emissions are rather on the higher end of these scenarios here. Next to the subsea permafrost carbon pool, there are also gas hydrates in the Arctic Ocean and on the shelves. This is essentially frozen methane, and it stores an estimate of minimum 20 gigatons of carbon. These gas hydrates are either locked within the subsea permafrost or beneath it. So permafrost sort of acts as a lid here. And as permafrost in the subsea environment is thawing, there's the potential to release these gas hydrates to the atmosphere. So this is a permafrost associated process which takes place here, which likely also increases the permafrost carbon emissions with this associated process here. Now I would like to move a bit closer to the coasts. They are really the interface between the subsea environment and the terrestrial carbon pool. We find two different sorts of coastlines in the Arctic Ocean. These are either bedrock coastlines, such as in Greenland, where there are mountain ranges along the coast, and on the other hand, unlithified coastlines, such as along most stretches of the Russian coastline and also in Alaska and northern Canada. So this is basically frozen sediment clasts, which hold together here the coastlines. Today the coastlines have an erosion rate of about 1 meter per year on average in the entire Arctic. Erosion rates can, however, be up to 25 meters per year. But as the sea ice continues to retreat, the ocean is warming, sea levels are rising, storms are increasing with intensities, for example, wave action is increasing, permafrost is thawing alongside with warming air temperatures. These coastlines are also getting even more prone to erosion, and the erosion rate is projected to increase 2 to 3-fold until the year 2100. Now the question is, which consequences does this have for the carbon emissions that are related to permafrost thaw? Now, all the organic matter that is being eroded from the coastlines is entering the Arctic Ocean, and the material is distributed here. The Arctic Ocean has a natural capacity for carrying dissolved carbon dioxide, so the Arctic Ocean acts as an atmospheric carbon sink. But as additional carbon is being released to the ocean through coastal erosion, the carbon uptake by the Arctic Ocean is reduced 7 to 14%, depending on the emission scenario. That's what's visualized here in the graph, until the year 2100. So this is, again, a permafrost-associated process which takes place here, potentially increasing the carbon emissions again. To the conclusions and outlook of my presentation. Permafrost is thawing, and old carbon is being mobilized in this process. In this graph down there, you can see from the 2019 IPCC report, the projected near surface permafrost area decline until the year 2100, which lies somewhere in the range between 25 and 75%. Permafrost carbon emissions are on par with emissions from industrial nations, which has shown the comparison which I've made in this presentation. But there are also processes that are related to permafrost thaw, such as the gas hydrates and the Arctic coastal erosion, which is not yet accounted for in these carbon emission scenarios. And the comparison with the 1.5 degree global warming goal shows that there's no room for additional anthropogenic carbon emissions. Every ton of CO2 that is less emitted to the atmosphere limits global warming. And with that, I am coming to the end of my presentation. I thank you very much for the attention, and I'm happy to answer any questions. Are there any questions? Oh.
What areas do you guys research a lot of
Me personally?
Yeah.
I personally work on the coastlines of Alaska, such as the northernmost tip with Kviatkvik, also known as Barrow, where we have really high erosion rates of the ocean, where we can also observe that the salt influence into the terrestrial environment is increasing. And additionally, I'm working in Kotzebue, which is also in the continuous permafrost zone of Alaska. And yeah, it's a comparably warmer and wetter region compared to the northernmost tip. So it's also potentially more vulnerable with ongoing climate change, this region.
So you have the graphs until 2100. Like I'm wondering, are there any projections beyond that?
This one, you mean? I guess there are from the IPCC report, not to my knowledge, but I can tell for the subsea permafrost, there are graphs, because like this tipping point, which we expect where the thawing processes of the subsea environment are accelerating, will be around 2100, when we really expect to have little to no sea ice anymore, at least during the summers. And after that, there will be a large increase of these thaw processes. So there are projections reaching, I think, until the year 2300, actually. Okay. Yeah. Then I think. Yeah. Thank you very much for your attention.